Yes, got it. Thank you.
All right, everyone. Come to today's logic session. We're gonna see the deduction rules for the various language constructs today, I believe.
Thank you. Okay, so we left out at the frame rule and the fact that the allocation was supposed to find some new thing that was not in the precondition. So one example of application of the frame rule is to verify this function. Say it's a recursive function that calculates that computes the length of a mutable list. So m length of p, if p is null, is 0. Otherwise, there is a recursive call on p.tl, and it returns 1 plus this result. So the specification looks like this. P points to L, m length of p returns some n, such that n is equal to length of L. This is the logic function. And we keep the list. So when we try to prove this, we can prove it by induction on L, not unsurprisingly. So in the nil case, you just add p points to m list of nil. So p isn't supposed to be null by definition of mlist. And so you start with an if. So if p is equal to null, you're proving 0. And the postcondition of 0 is lambda n is equal to 0. And so you have to prove this, which is fine. But in the case of the cons, I recall at the top the specification of the function. So you prove this by induction L. So assuming that L is equal to x cons L prime, you have this p points to L that unfolds to p points to x and p prime for some p prime star p prime points to L prime. So now you want to use your induction hypothesis, but your induction hypothesis doesn't have this whole thing as a precondition. It only has the green part. The p prime points to L prime. So you need to apply the frame rule at this moment to kick the red part out, to say, okay, I have only this as a precondition. I get the same as a postcondition with the fact that the result is equal to what I want. And then the frame rule gives back the red part and the postcondition. So typically, when you have when you reason on paper, you have to say, okay, I'm using frame on this. So if you want to draw all of the derivation rules, you'll have a hard time because there is a lot of things to be written. However, if you prove things in a proof assistant, you'll have something like this. So let me find length. This length. So that's the version in heaplang, the toy language of arrays. The spec is like this. You do something like this: induction L, a bunch of things when it's pure, and when it's nil, sorry, when it's cons, you're right here. You unfold, you do a bunch of steps, blah blah blah, blah 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 blah, and then you arrive to the point where you're supposed to apply your induction hypothesis, and so you do apply. This is the Irish version of apply of the induction hypothesis, and then you provide it what you give it. You provide the sets of hypotheses that you want to give it, and it will apply the frame rule automatically, because it's a very simple rule. There's no really need to that, but you still need to give it what leaves the heap, the heap predicates you have, what goes into the induction hypothesis, and then you get back what the induction hypothesis gives you back. So the induction hypothesis is here. So it's a pure cock induction hypothesis. It could be also an Harris hypothesis. It depends a bit on what you're doing. It's also a bit maybe hard to see here, but it's in terms of WPs. That's maybe why. And so yeah, so every time you do something like this, actually every time you do a load, every time you do a store, it applies the bind rule, the frame rule automatically. So you don't see it, it's just necessary for basically everything to have it. Yeah, okay. So back here, and yeah, and so the induction hypothesis had this form. The frame rule gave this. That makes sense, I guess. I hope. Please interrupt again if something is not clear. Okay, so then you can do some reasoning that is a bit more local. So for example, if you have if you want to reason about arrays, so in C, arrays are just a collection of pointers that are contiguous. So P points to array of L is the same as the big iterated conjunction on every index of the list L of P bracket I points to V, and P bracket I points to V is basically the same as P plus I points to V. So it's not a primitive construct, it's just derived. However, if you want to reason about ML arrays, like OCaml arrays, there are bound checks every time you do an access. So you have to store more information for your to prove your functions. You don't have just the collection of Pi points to V, but you also have some header information. P.length points to L, the length of L. And those are abstract definition. You're not supposed to inspect them to know what they are. You can only use them as they are and have some rules that are precise. So those are not really derived. You need to have some particular abstract definitions. What is interesting though is, so if you do this in OCaml, so that's maybe a terrible way to write some access in an array that is outside the bounds. So V is array.make 5, 0. So it's an array with 5 zeros in it. And then array.get V of 7 is accessing the index 7 in this array. So that's an exception. That is not a fatal error. You can catch it. And so this means that the precondition you have to have some, the precondition of your, access function must have some header information. So this one here. However, if you're proving your programs in separation logic, you know that you don't have bound errors. You know that you don't have out of bounds, because you've proved all your programs. So you could remove those bound checks, and when you prove your program, you can do OCaml opt dash unsafe and get slightly faster code. It's the same if you have if you had null in your programming language. You know, if you proved your program, that you won't dereference it, so you can have a bunch of things that you remove from your functions. A bunch of null checks. Yeah. Oh, yeah. Maybe that's fun. So when you have P arrow HD is equal to V in C, it compiles to dereferencing P plus HD is equal to V. And it's the same when you do P of I is equal to V. It compiles to P plus I. Take the cell at this point is equal to V, which means that you can also do the opposite. You can do I of P, which is a bit ridiculous, but it's the same. That works. You can try. And so when you reason about arrays, it's the same as reasoning about, access a normal cell. So you can do a star of P is equal to V. You need this rule for writing, this rule for reading, and all of the other ones are derivable from this one. Okay. So now it'll be a bit more about logic. I'll talk about heap entailment. So what is heap entailment? So first, we can notice that predicates have some kind of internal law. The star, you can combine two heap predicates and you get a heap predicate. And you have a few other items, a few operators to build some heap predicates. And on those heap predicates, you have a bunch of laws. You have associativity, commutativity, neutral elements with a pure heap. You have a law about extrusion of existentials. You can, if you have an exist, you can make the scope bigger as long as X is not in the part that is gotten eaten. You can extrude pure facts. If you apply it to a memory, you can say pure fact of P is the same as P outside of the memory application. And all of that assumes functional extensionality and propositional extensionality. Okay, so once you have this, you can have this pre-order heap entailment. So H1 triangle H2, so H1 entails H2. And that just means that H1 of M implies H2 of M for every M. So for example, R points to 6, entails there exists an N such that R points to N, and N is even. So this is useful to not manipulate heap every time you're using rules of separation logic. So it's a pre-order, it's reflective, transitive. Wait, it's a partial order, and antisymmetric. You have the frame property for entailment. So if H1 implies H2 prime, entail H1 prime, then you can extend both sides with H2. That's an example, that's fine. Now examples. So you have to focus now because I asked you which are true, which are false. Okay, what about the first one? Who think it is true? That sounds good. Very good. What about the second one? Who thinks it is true? Nope, it is false. You cannot have this bit. You can, if you have a heap that is of this size, then it cannot be of size 2, basically. When you unfold the definition, you will see that this heap must be decomposed into 2 disjoint heaps of 1 segmental heap and 1 segmental heap, so it must be just of size 2. What about the third one? Who thinks it's true? Okay, so no one's wrong here. Wait, no, there was a not a mistake, but it was a trap. So it's R point to 3 and R point to 4, so it's false. However, what about the fourth one? Yeah. Who thinks it holds? Okay. So it's false. It depends. So by the definition I gave, it is wrong. You don't have this because when you have a heap that satisfies the left part, it must have exactly the size 2, and the right hand side it must have exactly the size 1. However, if you're if you're working to Iris, typically you're allowed to throw things away, and then it's just true. You just think it just changes what it means to entails. But for now, and when I'm using this symbol, I don't mean the Iris entailment. That means many more things than what I showed you. So I'll keep it simple. What about 5? True? Who think it's true? Should be basic logic. So we have false on the left side of an implication, so it is true. What about 6? No one? Very good, it is false. What about 7? Many more people. True, indeed, because you don't have a separation between R and R, so it's false. Plus the values are different, so it is even more false. But even if the 4 and 3, even if 4 equals 3, it is also true because it's not separated. Okay, very good, thank you. So there are some rules to reason about entailment. So you have some rule to introduce the existential on the right. You have some rule to introduce pure facts on the right as well. As long as you know P, you can have P on the right. So that's an example. You have R points to 6. R points to 6 implies there exists N, such that R points to N and N is even. So how do you prove this? Typically, you start on the right. You have to find some N, so you instantiate it with 6, probably, because you have 6 on the left. Then you introduce the pure fact on the right. You're using math to prove that 6 is even. And then you're using the reflexivity rule to prove that R.6 entails R.6. Okay, so in general, so suppose you have this thing that you know it's true, but it's maybe you don't know which rule to apply first. Yes.
Sorry, before we went much further, I wanted to ask something about the previous one. No, so actually, the examples there that you said that they have to have the same size.
Yeah.
Is that because of the way you define the implication, or?
Yeah, so the implication is very simple. It's just this way. It is also you could also have something like H1 of M. I mean, it depends on a bunch of things. You could define this as any heap that has domain R, such that the heap value at R is 6, and then it will hold. I choose to make it simpler.
Because it has to have exactly that.
So yeah, so typically in the separation logic of lectures of Hoare and Brooks, you have like two symbols, one that includes everything, one that is restricted to that. You can have both.
Okay, yeah, thanks.
Yeah, so if you have this big implication, typically you have some I mean it's basic logic, I guess. You typically try to extract everything you can from the left, and then you build things from the right to the right. So to prove this, typically you first need to know which n it is, and then to choose which m it is. It would be. Yeah, that's, I mean, it's logic, so I won't do it. Okay, more examples. Only 5 of them. What about the first one? 1, 2, 3, 4, many. Okay, you can count up to 4. True, very good. What about the second one? 0, very good. False. What about the third one? Maybe I need to squint a bit to remember what I wrote. Anyway, who thinks it's true? Yeah. Very good. It is true. What about 4? Yep. Very good. What about 5? Slowly rising hands. Yes, very good. It's true because it's implying false. So it's true. All right. So oh yeah, that's what I wanted to tell earlier, but now it's a bit clear. So if suppose you have this big entailment, typically you would extract from the left-hand side. So here you extrude the existential quantifier, and then you apply the rule for existential, you apply the rule for the pure facts, and then on the right you do the same. So you come back on the right. Okay, so that was a heap entailment. So very good job. You deserve a coup. Very nice. So it was good to give you some strength for the structural rules. So we've seen the frame rule. Yeah, there was some question about this star here. Does it, includes this X? So no. A reformulation of this frame rule is more. It looks more like this. This is more precise. Like H2 is combined normally with this normal star to the left, but when you're talking about the result, H2 is not allowed to talk about the result. So typically, the typing makes sense only if you do this, but even the logic also makes sense only if you do this. So Q weird star H is the same as the function that maps X to Q of X star H. So X doesn't go into H. Now that we have heap entailment, we have the consequence rule. So it's like the same as in Hoare logic. You can, if you have a precondition that is implied by the current one, you can use it. If you have your postcondition that implies your current postcondition, you can use it as well. And of course, you have to overload to talk about the postcondition as well. So it entails Q if it's pointwise. Yeah, so it doesn't, you don't garbage collect here. It must be the same footprint on both sides. You don't throw things away. However, if you do want to throw things away, you have to have some rule to talk about garbage collection. So if you have the same example, so you allocate a reference to X, you allocate a reference to this reference, and then you throw away the new reference. So you have this post condition. You want to have this specification. So how do you go from the first specification to the that we can prove to the second specification that we desire? So the question is, can the following rule be used? Who thinks it can be used? No one? Can somebody tell me why? Who thinks it cannot be used? Oh.
What
Yeah.
if H prime is just like false or something?
I mean, if you can prove false, you can prove Q, that's fine.
Means the shape.
Yeah.
Might enforce a certain size of the stack, or in H. The post condition might enforce a certain size of the stack in H, and by dropping it, you no longer enforce the same size.
Yeah. So that's a good point. It's assuming you have indeed triples that allow garbage collection. So there is a version of this rule is true, but you cannot use it to prove the second specification for the first one. So that's the question I'm asking. Why cannot I use it? Yeah.
Because R is free in the right-hand side.
Exactly, because R is free in the right-hand side. So this star it's kind of important that it doesn't talk about the return value. And so this cannot be used to prove this because this R is cannot be used in H prime. Okay, so the real rule is this one, HTQ star GC, and GC is the exist H prime dot H prime. You can also call it true because it's true on all heaps. So if you unfold it, it's the same as the following. Lambda x, qx star, there exists H prime such that H prime. And so in this case, you can instantiate H prime as there exists an S so that S points to R. It's fine. You hide the X behind there exists. It does depend on the heap, but that's fine. That's supposed to be the case. Okay. Okay.
So is it
Yeah.
a typo in the rule that you're using the weird star at the top?
Weird star is not a typo. It's this star. So the X is not going there. However, every heap can satisfy the GC, even the things that mention X.
I'm confused. When do you switch the meaning of triples to mean this weaker garbage collected thing?
I mean, the third interpretation of triple that we had last time included throwing stuff away at the end. Like there is this M3 such
Okay.
that, I mean, it's not included in the post condition. So you can have with or without, that's fine, you can choose, but in the case where you have, you need to have some rule to actually,
So just this section of the lecture, so we're gonna keep this interpretation for the rest.
So
Because
I'm typically keeping the GC rule, yeah.
you are including it.
Huh?
You typically including it.
Including it, but it's not in the heap entailment though,
Thanks.
even though in RS it is. But it's not called entailment, it's like another symbol. Yeah. So you could have also this version when you remove it from the precondition, but you can derive it from the previous one plus the frame rule, but that doesn't matter. Yeah, you have the same rule as exist and prop for entailment as you have the same rule also for the triples. Okay. Okay. And you don't have it in post condition because you can use it for with the entailment, but not in the precondition. Okay. So finally, for terms, maybe that will be a bit more concrete. Okay, so when you want to reason about sequences, you need to have a rule for it. So if you have inc of R, so increment R by 1, and then bang R, get the value of the reference R, you need to have, you probably want to have some specification like this, R points to N, and at the end we have N plus 1, and R is incremented by 1. So you need to invent a post condition for the first part. That will be the precondition for the second part. So the rule that corresponds to it is the following. So that's the same as in Hoare logic. So I mean, there is one subtle difference, is that you need to talk about the return value, and for sequence, the return value will be ignore, and it will just be unit. So if you have a HT prime, T1 Q prime, then the precondition of T2 will be Q prime of unit. Okay, so what will be more interesting is the let binding. So if you have H as a precondition for let X is equal to T1 and T2, what are the preconditions for T1 and T2? What are the specifications? So that's an exercise. So it's a bit easier if we, do it together, I think. So we have let X is equal to T1 in T2. We have H at the beginning. We have Q at the end. Okay, so what should I have as a precondition for T1? Yeah.
H, right?
H, perfect. What about the postcondition? Choose something, Q prime. Okay. So now what about, so we need to have something, so there are a bunch of indications. We need to have something about T2. So the difference, the difference between T1 and T2 is that T1 has a new variable, it has X. So we need to talk about X. So it is present in T2, so it probably must be present in the precondition as well. Otherwise, we won't be able to talk about it. So we do something, we do have to talk about it, and it could be a bunch of different things. So for example, if T1 was not deterministic and returning some value that is either 0 or 1, you need to be able to talk about those two things. So you have a for all X, and then what do we have here?
You have some spec for X.
Yeah, what is the specs for X?
Yes, T1 evaluates to, so H implies H, triangle. T1 evaluates to X.
Okay.
Something like that.
Yeah. What else?
And Q prime holds, Q prime holds for X.
Yes, so that's a good thing. So in fact, everything that you want to say about X, you should say it in Q prime. So in fact, you just have this. So if you have some very interesting information about T1, I would say it evaluates to X, you should write it in Q prime. That's the best condition of T1. That's everything you want to know about T1. And what about the post condition?
It's not mentioned.
Just Q. Perfect. So it is that indeed. I will be, so that's the rule. I recalled it in red. So the exercise now is to instantiate it for this particular program, which is it's very simple. You have R points to 3. Let A is equal to bang of R in A plus 1. Okay, so we have this. Let A is equal to bang R in T2 A plus 1. That is A here. H is R points to 3. Q is, what do we want for Q? Huh? Which we want to choose.
So yeah, lambda B is equals to 4 and R points to 3. Like it.
Yes, so lambda B is equal to 4. And we don't want to lose our precious reference.
It's now behind you. Can you move a line down?
Ah, thank you. Okay, so we have this as our post condition. So I'll just move this here, this needs to be Q. H is here. T1 is bang R. Q prime is to be determined. We'll leave this X here. Okay, so what should be Q prime? Lambda A is equal to 3. That's it. Yes, and R points to 3. Thank you. So we'll just replace this here. So Q prime is now this lambda. So we can beta reduce it to this. In fact, I should not have done that because T2 here talks about A, so it needs to be this A. So I'm put A here, and in fact, this is A plus 1. So some beta reduction. Oh. Okay, and that makes sense because A plus 1 can be proved to be equal to 4 if A is equal to 3. Okay, so thank you for staying with me. So that was the answer, but of course, yeah, it's better to go through it slowly. Okay, now a reasoning rule for values. Well, so the reasoning rule for value is very simple. It's empty fact, empty heap the value, we return some return value that is equal to the value. If you have some heap as a precondition, you might not want to invoke the frame rule and then apply the rule for value. So there is a rule for value that is a bit simpler, which is if someone can guess maybe what are the things that are on the left and right of this triangle. H is good. Someone else for the right? Yep, Q applied to V, perfect.
Surely times garbage collection.
You can apply it later, but when you have a value, it may be not the time to throw things away. I mean, you can apply it later. You have a bunch of that if it's the end of a function return, maybe. So yeah, you could include the star GC if you want here. Okay. There is a rule for if. It is not very surprising. So you prove HQ as pre and post for an if you can prove it from both sides of the if for T1 and T2, assuming that V is true for T1 and assuming that V is false for T2. There are a bunch of equivalent formulations with ands and ors, but are equivalent. There might be some, there is some restriction here that is V is a value. So typically what you do, if you can, but you cannot do that in all of the cases. So if your language has a band rule and you can replace any variable or any expression by value, then you can do this and apply some transformation to a normal form. So every time you have something that is not a value that is in position of a red X, you say let V is equal to this expression in if V then T1 then T2. So that way you can apply first the rule for binding and then the rule for the if. So you don't have to have a very complicated rule for if, because otherwise if you have an expression that does some side effects, then you need a much more complicated rule for if, which is necessary sometimes. It depends on your language. Okay, so say you have a function application. So you have V1 applied to V2. Again, you can transform to a normal form with a bunch of lets. So if you have a function lambda xt applied to a value V2, the rule is just to apply it. And so you get this, basically you get a reduction from V1, V2 to T in which V2 replaces X, and you just prove it for it. So there is nothing going on. It's just a beta reduction. In general, if you have a deterministic beta reduction, or not beta reduction, a deterministic reduction, you can exchange between the two things. So if you have if you have x reduces deterministically to y, which is defined by x reduces to y and everything that x reduces to is equal to y, then you can exchange x and y in any triples. So if you want to specify a simple function like inc, you would do something like this, specify it on all of the arguments. And so when you want to verify it, you just replace the content, the body by the in the body you replace the argument by the value you provided, and you verify this. So there is nothing going on. Yeah. So if you have a recursive function that is exactly the same, it's not a smart rule. It is just, again, the beta reduction of v1, v2 to the body, in which we replace the argument with v2 and the function itself, the function name itself, with the function parameter with the value of the whole body and the whole definition. But so when you want to specify to prove a recursive function, then you do induction on something else. You're not doing so if you have a function on list, you do recursion on list, and etc. If you have something more, if you want to allow yourself to do non-terminating recursive calls, and we'll see that later. Again, that's pure deterministic. Okay, I'll just skip this. If you have local functions like let rec fx equal body in T, you might want to do this. The hypothesis about f is this, that you would prove in the normal ways with what we've seen before. And the rule for this is you name this your hypothesis on f, and you use it from let rec fx equals body in T. You go right away and prove things to T by just having some hypothesis that f is indeed can be expanded to its own body. Okay, so rules for all of the language constructs. Basically, I mean, maybe there are a bit more. Yeah, you can have also loops. So you have a rule for loops, but that's very not surprising. For a loop, you need to have an invariant. So for a for loop, you have an invariant that depends on an integer. You can be a bit more general in case the A and B are not in the order that are usually in order. The rule for the while loop is typically something like this. However, in our language, we might want to have some effects in the condition or some access to the heap. So we need to have a bit more than just the invariant. You need to have an invariant before the condition, after the condition. So it's a bit of a mess. Also, it seems like we're doing some work that is not useful because like for the recursive function, you didn't have a rule for it. It's you can just expand it. So in fact, what we do typically, like in arrays or like in arrays, a bunch of other things too, you have something that you just expand again. So if you have while T1 do T2, you can just prove that the same holds for if T1 then T2 while T1 do T2 else unit. And if you can prove this, it's the same as proving this. So it's again a case of deterministic reduction. And then you're using the mechanics of your logic to compensate for the fact that you're not actually using subterms. So in this rule, at least it has the merit of having only having hypotheses of your rule that are using subterms of what you had. So that's good. But it's not something you really need when you're doing proofs. It depends on your framework, but typically you do this. Yes, Guillaume.
So when you're trying to prove the while loop with the big inference rule, you have to come up with an invariant.
Yeah.
But if you're doing this one-step unfolding, you don't have to. So it feels like you're cheating somewhere.
Yeah. So
where is the invariant ending up?
So for this, you would at the time where you apply the while rule, you need to come up with actually two invariants, I and j, and so you need to think hard right now. For this, you don't need to think hard. For example, if your loop is running only 4 times, you just expand, expand, expand. However, if it's not like that, if you have like a n that you don't know, you need to think a bit more before unfolding, 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 of course. So you would do, okay, let's stop now, let's do an induction, terminating or otherwise. And you need at this point to say this, my current triple will be enough to prove my induction, otherwise you have to generalize. So yeah, no magic. There's an example with a while loop, but maybe, I mean, you can use also when you're proving a while loop. Oh yeah, what that helps. So having this kind of forbids you to use the frame rule. So, I mean, if you really need to remove something every time, it cannot fit into the invariant because you need to put it back every time. So when you use this rule, it's a bit more flexible. So in this example, when you're proving this function length that uses a while rule, you can use the frame rule inside. So okay. All right. So now, so something else. Suppose you have a function that has some local state. How do you specify it? So you have let r is equal to ref of 3. You have a function that just increments r. How do you specify it? So say you have I mean, we won't even specify it. We're just having some examples. So f of unit, bang r. And so every time, so you start from r points to 3, and you go to r points to 4, r points to 5, and the specification of this function that has some local state is just, you talk about the local state. So that's fine. That's easy because you know the actual reference. When you do let r is equal to r to ref 3, you know the value of r, you know the location. But suppose you have some really local state, so you're making a counter function. So let make counter unit is equal to let r is equal to ref 0 in the function that increments the reference and returns the value. So how would you specify this? So how do you use this function? You said let c is equal to new counter, let x is equal to c, let c of unit, let y is equal to c. So each time it will be incremented by 1. So at the end you have x is equal to 1, y is equal to 2. So how do you specify this? You cannot talk about the reference value because you don't know it when you specify this counter function because it doesn't exist even yet. When you specify make counter, you don't know you don't have a particular reference because it will be a new reference every time you apply this function. So you define this weird representation predicate. F points to count of n. So you can imagine it like this. F points to some structure. So it's not really a data structure. Even, I mean, it is kind of a data structure. It's just a symbolic one. Inside, there is a real data structure, just a reference. R points to some integer n. And F can be specified in terms of R. So there exists R points to n, and some pure fact that contains a whole triple in which for every I, if R points to I, we apply F, R points to I plus 1, and it will return I plus 1. And so now exercise, but we'll go a bit quickly. So how do we specify this? So that's just a counter data structure, basic representation predicate at least. So when we specify the function make counter, we say that we don't require anything as precondition, and we return an f that satisfies count of 0. And so and then we need something. I mean, we could unfold the count of 0 to use it every time, but we can also specify this f, like in the post condition of this, we could add for every f and I, if actually it's not in the post condition, it's just property of count. For every f and I, if f points to count of I, when we apply f, we get back f points to count of I plus 1. So we package things up in a representation predicate. So that's quite common. Okay, let's see some higher order functions. So what is the first higher order function that we could have?
Hidden, map,
Oh, apply.
by
So you have apply f of x is equal to f of x. How do you specify it? Like this. It is very simple. What is the second?
Map.
No. Oh yeah, you could also write it like this, like move the triple inside the precondition. Twice. So at least this one talks about the heap a little bit. You apply a function twice. So you could write it like this. So it's again basically kind of unfolding. So if you have a function repeat, so it's a higher function because you have a function as a parameter. So how do you specify repeat? You have a function f that you apply n times. So then you need to have an invariant. You say you start at I0, you end up with I of n, and your function is supposed to make you go from I to I plus 1. I of I to I of I plus 1. Okay, so let's say you have some iteration and you have this function iter. This warning signs is about, so now we're doing pure lists. Because mutable list are slightly harder, but it's just not relevant to this. So if you want to reason about iteration, we're just using pure lists, like OCaml lists that are not mutable. So we don't need to reason about them. So it is as if they didn't live in the heap. Of course, most of your lists in OCaml are living in the heap because you need to allocate them. You don't know what they are at static time. Some of the lists can be allocated not on the heap, but most of them are. Okay, so to specify iter of f and l, so it's not sorry. It's because it's we talk about the state. Yeah, I'll just go to the answer. So how do you specify iter? We could do it in this way. So be warned, there will be a bunch of different ways. This is maybe the simplest one. You start from I of nil with some invariant I, and you end up in I of L if you apply it to L. And then your function goes from I of k to I of k snoc x, because you add it at the end. That's one way. However, you might not be able to prove all of your functions. Yeah, so you have a bunch of examples. Maybe I'm going too fast because it seems easy. You can also stop if something's unclear, of course. So this is an example. You can compute the length function by using a reference and the iter function. And the iter does fun x arrow increment r. You apply it to the length, to the list. And so you need to come up with an invariant I, and not surprisingly, I of some list will be just r points to the length of this list. So you start from r points to 0, and you get to r points to the length of it. And your inc function is an instantiation. The specification is an instantiation of its specification usually. Yep. So that's an exercise. Blah blah. So say you want to be a bit more constrained. So say you want to compute this very smart, very complicated formula, in which you do division on the elements of the list. So why division is because you need to know that if you want to prove your program correct, you need to know that all of these values are not 0. And so if you need to prove this function, the specification that is above that we've seen before is not enough, because in the top, you don't know that x is not 0. So how do you do this? You need to specify a bit more. So one way is to add, oh, wait, never mind. This x should be in L. So then you have enough information to know that it's not 0. So not surprisingly, this is not enough for all of applications. So say you want to compute this fraction, then you need to know the specific order in which the function f is called, because otherwise you won't be able to prove that it's not 0, by which you're dividing. So in this case, you can have this a bit bit more complicated hypothesis on K that says K is a prefix, K snock X is a prefix of L. You can prove it iter. Let's skip this. You can also have a specification that talks about the remaining items. It is sometimes much easier to use. It is also easier to prove. So you assume that X, wait, no, that's the old one. And then we want the new one, so it will be something like this. So if you want to talk about the remaining items you need to iterate on, you start from L and you end up to nil. And your function, instead of adding to the invariant, it's removing from the invariant. Okay. So this one is more general than all of the other ones that were before. However, if you want to have if you have some iterator on not a list, something that is not deterministic, and you don't know, I mean, you cannot know at the beginning which will be the order, because maybe you'll depend on some input from somewhere. You need something a bit more elaborate to talk about iterators. So if you want to know more, you can go see these two papers in which you have 2 predicates, enumerated and completed. Enumerated is just for your current iterator, what are the things that have been seen before? And completed is a predicate that says when you're done. Okay, so there is an example of iterating over a mutable list. How do you do this? So iter of f of L, but this time L is not a pure list. It's just it's mutable list. So when you do this iteration on this mutable list, in fact, it does not change the structure of the list. So you add the predicate mlist just next to your invariant. The emitter function does explode the structure, but does not modify it. So it just is transferred from the precondition to the postcondition and does not change anything else. Yeah, I skipped a lot of function about fold and everything. But if you have a more complicated function that iterate on lists, you can have invariance over 2 elements, one list and another list that will be the result, for example. You can do it. Okay. Yes.
So what if I want F to be able to borrow the list, the mutable list?
F to be able
to borrow the mutable list, like to.
So F, we'll see that it borrows the elements. You want like the function F to modify maybe the list? You'll need to prove a different specification. It's also kind of hard to have a specification for that. It could be, I mean, probably that in this case, you will not want to use this and just use the unfold every time and not have a specific version of iter for your application. That is a little bit strange. Okay. That should be quick. Yes, Ohad.
So something qualitatively different happened here, right? So you're kind of reflecting the semantics of the whole language, right, into a single judgment. Where previously you were kind of reflecting just not in this specific example, the high order separation logic, right? So in order to specify a function, you say my maths have to be able to talk about the semantics of the whole function, all possible functions, right? In this language, right? So, and the soundness of board triples. It feels like you're throwing a lot more than what you previously did into the predicate language. I mean, you're doing it in Iris, which is kind of like a set theory, basically, with little stuff in it. But maybe we should talk about that offline.
Okay.
Sorry for rambling.
Okay. That's probably fine. I guess I can stop. Yeah, maybe a teaser for next time. We'll see, but it's not really hard, but it's useful. So you remember mlist, which is the predicate on mutable list. But if you have like list of lists or list of trees or list of references, how do you talk about those? So you could say, oh, it's a list of values, and then I specify all of those values next to it. But the more compositional thing is to have an M list of predicates, and then you can compose those predicates. And I mean, it's better. You just have to think of doing that instead of packaging things separately from your predicate, just on list. Okay, I'm done for today. So thank you. Okay.
Lunch.